Now, in order to understand this one is not that difficult, but the one of the hydrogen is really more interesting. It all originates with the idea of what is called the Runge-Lenz vector, which I'm going to use the last 5 minutes to introduce, and think about it a little. So it comes from classical mechanics. So we have an elliptical orbits, and people figure out there was something very funny about characterizing elliptical orbits. So consider a Hamiltonian, which is p squared over 2m plus v of r, a potential. The force classically would be minus the gradient of the potential, which is minus the derivative of the potential with respect to r times the r unit vector. Now, classically, this all begins classically. So it's, except for spin 1/2 systems, classical physics really tells you a lot of what's going on. So classically, dp dt is the force, and it's minus v prime over r, r vector over r. And dl dt, the angular momentum, it's a central potential. The angular momentum is 0. Its rate of change is 0. There's no torque on the particle, so this should be 0. Now, the interesting thing that happens is that this doesn't exhaust the kind of things that are, in fact, conserved. So there is something more that is conserved, and it's a very surprising quantity. It's so surprising that people have a hard time imagining what it is. I will write it down and show you how it sort of happens. Well, you have to begin with P cross L. Why you would think of P cross L is a little bit of a mystery, but it's an interesting thing. Now, here is a computation that will be in the notes that you can try doing, and it takes a little bit of work. So, but it's algebra. You know, if you compute this and do a fair amount of work, it's like 5, 6 lines, I would suspect it's fairly non-trivial to do it if you don't see how it's being done, but it will be in the notes. You get the following thing. Just by manipulating the time derivative of P cross L, you get this, which is equal to m times the potential differentiated times r squared times the time derivative of this. So time derivative, you can get a conservation if this is a constant. So when is this a constant? If this is some constant, say e squared, you would get a conservation. But what is v prime equals e squared over r squared would give you that v of r is essentially minus e squared over r. That's the potential of hydrogen, or the 1 over r squared, 1 over r potential, 1 over r squared force field. So in 1 over r potentials, this is a number, and then you get an incredible conservation law, ddt of P cross L minus m e squared r hat over r is equal to 0. So something fairly unexpected, that something like this could be conserved. So actually, you can try to figure out what this is. And there's two neat first, one thing that people do, which is convenient, is to make this into a unit-free vector. So define R to be P cross L over ME squared minus R vector over R. This has no units. And it's supposed to be conserved. Now, one thing you will check in the homework is that this is conserved quantum mechanically as well. That is, this is an operator that commutes with the Hamiltonian. Very interesting calculation. This is a Hermitian operator, so you'll have to Hermiticize the P cross L to do that. But it will commute with the Hamiltonian. But what I want to finish now is with your intuition as to what this is. And this was a very interesting discovery, this vector. In fact, people didn't appreciate what was the role of this vector for quite some time. So apparently it was discovered and forgotten and discovered and forgotten like 2 or 3 times. And for us, it's going to be quite crucial because I said to you that this operator commutes with the Hamiltonian. So actually, you will get conservation laws and will help us explain the degeneracy of the hydrogen atom. So it will be very important for us. Now, how does this look? First of all, if you had a circular orbit, how does it work? Have a circular orbit. Let's see. P is here. L is out of the board. P cross L is here over ME squared. And the radial vector is here, the hat vector. So the sum of these two vectors, P cross L and the radial vector, must be conserved. But how could it be? If they don't cancel, it either points in or points out. And then it would just rotate, and it would not be conserved. So actually, for a circular orbit, you can calculate it. See the notes? That actually is an easy calculation. And you can verify that this vector is, in fact, precisely opposite than this. And it's 0. So you say, great, you discover something that is conserved, but it's 0. No. The thing is that this thing is not 0 for an elliptical orbit. So how can you see that? Well, here, at this point, P is up here. L is out, and P cross L, just like before, is out. And R hat is in. And you say, well, OK, now the same problem. If they don't cancel, it's going to be a vector, and it's going to rotate. But it has to be conserved. So actually, let's look at it here. Here, the main thing of an ellipse, if you have the focus here, is that this line is not, the tangent is not horizontal. So the momentum is here. L is out of the blackboard, but P cross L now is like that. And the radial vector is here. And they don't cancel. So the only thing that can happen, since this is vertical, it's a little bit to the left, is that the R vector must be a little vector horizontal here. Because the sum of this vector and this vector, the thing that it has to be horizontal. Here we don't know if they cancel, but if they don't cancel, it's definitely horizontal. We know it's conserved, so it must be horizontal here, so it points in. So the Runge lens vector, R, points in, and it's, in fact, that. So here you go. this is a vector that is conserved, and its property is that it's really about the axis of the ellipse. It tells you where the axis is. In Einstein's theory of gravity, the potential is not 1 over r, and the ellipses precess, and the Runge vector is not conserved. But in 1 over r potentials, it is conserved. The final thing, sorry for the last taking so long, is that the magnitude of r is precisely the eccentricity of the orbit.